Right, let's look at this balls exercise. So there's not much to go on in the description, and that's because it's a difficult problem to describe. If you are given all these equations, you're basically given the entire program. And that's really all this program does. It updates a lot of variables and then draws the current state of affairs. So let's just have another look at what it looks like. There are all these balls, they bounce down, they collide with each other. You can see they're always moving, jittering a little bit until they settle down into roughly level, and after 20 seconds the simulation just stops. Right, so I'm not going to write this code from scratch. We are just going to work through the program. This is an important skill, to be able to take an existing program and analyze it and figure out exactly how it works, what the parts are. So here's the program, but I prepared a colored version which will help us a little more. So let's start with these global variables. Firstly, there's width and height of the canvas, and these could have been constants, but the idea was originally, I think, to read all of these from a configuration file so that the user can customize it, but at least for now we don't have that feature. Then there is count, the number of balls. There's a variable called TC, which is a time constant, which is not exactly clear now. There's X acceleration, so horizontal acceleration, and it says here wind. There's Y acceleration, vertical, which is just gravity. Then there are these green variables, which I don't think show up very clearly. Vx, Vy is the ball velocity, and these are all arrays of doubles. Px, Py is the positions of the balls. R are the ball's radiuses, and M are the ball's masses. So we have an array which will initialize to be of size count, I guess, which hold all this information for these balls. Then there is E, which is coefficient of elasticity, and that's probably for, I know it's for when balls collide, they bounce back with a certain coefficient. So the collisions are not perfect, there's some loss of energy. There's also something called max radius, which is the largest radius of any ball. Okay, good. So let's have a look at main. Main starts by calling initialize, which I guess will initialize these variables. There's a time variable, which is 20 times 1000, so that's probably 20 seconds times 1000 milliseconds to give us a total time of 20,000 milliseconds. There's FPS, which almost always stands for frames per second, so we're going to display 40 frames per second. Then there is a starting time, which is set to the current time in milliseconds. This function returns the milliseconds since a given date in history. In fact, it's the 1st of January 1970. This is a common starting point for programming languages and operating systems. The stopping time is the starting time plus the time the simulation will run. Then there's also the update time. This is the time when the next update will occur, and it's the starting time plus, so this is 1 second, this is the number of frames per second, so this is number of milliseconds between updates, between frames. So the next update time is the starting time plus this constant. And the current time is the same as the starting time initially, which is just the time now. And then we have this while loop. Let's see. It repeats while the current time is less than the stop time. That makes sense. So while we haven't reached the stop time, we're going to keep on running. And as you can see, this is using real time. Clock time, wall time. It's not using some kind of artificial time just a counter. If the current time is more than the next update time, we are going to update draw the next frame. So it starts by calling update balls, and then it calls redraw with the elapsed time. The current time minus the starting time is the number of milliseconds since the simulation started. And then it updates update time. So the next time we're going to update is the current time plus that constant again. Good. And at the end of the while loop, it always sets the current time to now. And this will keep on going until we've reached the stopping time, so 20 seconds from now. Right. Okay, so the main function is not hard to understand. It does some kind of initialization by calling function initialize and update, initializing a lot of time variables. And then it has this while loop, which just updates the next frame when necessary. Let's have a look at initialize. There it is. Let's do that. So let's see what it does. It says count is 100. So we can have 100 balls. It sets the width and height. Then it calculates the max radius as the minimum of the width and the height. So if the canvas is really wide but not very high, the maximum ball that can fit in there is the minimum of the two, which is the height. That'll be the minimum radius. Or if the canvas is very narrow and very high, the minimum of those will be the width, and that's the radius of the max ball. But it also divides it by 35, right? So we're going to have a lot smaller balls, and this is once again arbitrary. There's no reason for 30. We can change it. We can play around with this simulation a lot. Then it says ball area is pi times max radius squared. So that's the area of one biggest ball. The total balls area is number of balls times ball area. So that's the area occupied by all the balls together at most. The window area is the width times the height times 0.75 rather. So I'm guessing we never want more than 75% of the area being occupied by balls, because otherwise there are too many of them and they can't move. The simulation won't really do anything. If balls area is more than window area, so the area of the maximum area of the balls, we've calculated that, is more than the area we want occupied, we adjust count. So so that this constraint is satisfied. Balls area should be less than or equal to window area. Okay, so that's initializing basically just the count and the width and the height. All of this is just for those three variables. Then the purple code is going to initialize the balls, it seems. Firstly, we start by setting x acceleration to 0. There's no wind in this simulation. We can add that as well. The y acceleration is 0.01. That's supposed to be gravity, and if you know the real acceleration due to gravity is 9.8 meters per second squared, but this is 0.01. And the reason for this is that even though the time aspect of the simulation is very real, the physical aspects is not that real. I mean, for one, we are simulating two-dimensional balls instead of three-dimensional balls. So it's not unreasonable to expect that this won't be the real gravity constant. And in fact, I think this value was reached by fine-tuning it. We can make gravity stronger or weaker. And if it's 0, the balls will just float around a little. The elasticity coefficient is 0.93. That's quite reasonable. And here it says sets time constant to 2.0. That's arbitrary. I'm not exactly sure what will happen if we change this. I think the balls will just move in slow motion, but it's not perfectly clear how we reach this, probably also just through fiddling. Then it creates the array of masses, the array of radiuses, the Vx and Vy, the velocities, the speeds of the balls, Px and Py arrays for the positions of the balls, and then it's going to initialize the ball. So let's see what it does. I starts at 0 and goes up to count. the position of ball I is some random number to the power of 2.5 times the width. So let's just see. Math at random will be between 0 and 1. 0 to the 2.5 is 0 times the width is 0. So the ball's going to be on the left, and 1 times 2.5 to the power 2.5 times width is 1. So that's just the width. So in essence, the balls can lie anywhere, and this is just biasing them to lie a little bit to the left, so that they're not as evenly distributed as we might think. The Y position is just anywhere on the Y-axis. The velocities are both from minus 0.1 to plus 0.1. We've seen this construction before. The radiuses are, well, if math at random is 0, then this is 0.6 times the max radius. So balls vary from 60% of the max radius to, this is 1, to the full max radius. So they've got a random size from 60% to 100% of max radius. And the masses is this funny formula, which is really the formula, this r cubed times pi is really the volume of a sphere of radius r, and it's multiplied by this arbitrary factor, which we can think of as the density of balls. But the reason for this is just so that we have realistic masses. The balls won't really be three-dimensional. Okay, right, so that's the initialization of the balls. And then lastly, it sets the canvas and sets the x and the y coordinates. So initialize is longish, but not hard to understand. Okay, what's next? Next we have to look at update balls. So let's go down here. That's redraw. This is update. So I can tell you that update has three parts. It checks for collisions, because when we have to take into account what happens when balls collide. They can't just move through each other. It forces all balls to be on the screen, and then it applies gravity to all balls. So let's have a look at this second part first. It starts at 0, this time the variable is called A, goes up to count, and then it just says if the x-coordinate of ball A is smaller than its radius. So that means it's right on the edge. In fact, if it's smaller than or equal, it's the center point of this ball is either off the screen or right on the edge. It resets it to be exactly on the edge, and it multiplies the velocity by -1, so it's now moving backwards, multiplied by elasticity. So it's as if the ball bounced against the side of the window. And we reverse the x component of the velocity so that the ball starts moving backwards. So the ball was moving towards the wall. We detected that it's off the screen a little bit, and now we're moving it back. And these other four ifs do exactly the same thing, except for the other sides of the window, even the ceiling. So balls can bounce against the top of the window as well. This is just for keeping the balls on screen. If we didn't do this, they'd be bouncing and disappear off the screen. Some of them at least. Okay, right, let's see the last part, because the collisions is the difficult part. So for all the balls we do the following. We add to the velocity the x and y accelerations multiplied by the time constant r. So this is where the time constant comes into play. So it's just updating the velocities based on the acceleration, and it's updating the positions based on the velocities. So we're just adding basically acceleration to the velocity and velocity to the position. And the time constant is simply because we're only showing 40 frames per second. A ball is really moving in that time. So if we didn't multiply it by some kind of constant, we would get a kind of slow motion effect where the time from the ball's point of view is moving fast or slow. We can play around with this and speed it up and down. But let's have a look at the collisions. So what does this do? There's an outer for loop that goes over all the balls, starting from ball 0 up to ball count. Then there's an inner for loop that starts at a plus 1. So if I'm looking at, let's say, ball 5, a equals 5, then b will start at 6, 7, 8, 9. And then if a turns into 6, b will be 7, 8, 9. So it's taking the balls one at a time and looking at all the balls that follow this ball. This is because we don't need to compare two balls that collide more than once. So every ball I'm comparing with those that follow, and then I don't have to compare it with those that came before it, because when I was handling those balls I'd already checked that ball B and A are actually did they collide. Right, so DI is difference in x times difference in x plus difference in y times difference in y. So D1 is the distance squared between the two balls, and D2 is the sum of the radiuses squared. If you remember from the random tiling work, if two balls touch, then the distance between their centers is equal to the two radii, the two radiuses added. So this is just the square of those distances, and we're not calculating square root because it's an expensive operation and we don't really need it. I mean, let's say D1 and D2 are equal, then we know that the square roots are equal as well. So we don't need to compute the square roots, at least at this point. It says if D1 is less than D2, so they're closer together than the sum of the radiuses, so they are overlapping, they are colliding. Now we calculate the square root. So we get the real distance DI. DD is the sum of the radiuses minus DI. So we're calculating by how much they overlap. And if you think about it, if two balls collide gently, they won't overlap much because they're both moving slowly. But if they're moving fast, they will overlap a lot. So DD is going to give us some indication of how hard they collided. And then there is CDX, which is the X component of their overlapping, and CDY is the Y component of their overlapping. And we just add that back to their positions so that we're basically separating them so that they're just touching. So this just adjusts the positions so that they're no longer colliding, they're just touching. Then it takes their masses, MA and MB, and their velocities. So this is just a neater way to write quite complicated formulas that follow. And in fact, I'm not going to go into these formulas. These come from physics, and they simply tell us how the velocities will change when two balls collide. Perhaps the most important part is that it's all based on the difference of their masses. So the preservation of momentum tells us that the momentum of two balls, the mass times their speeds, must remain constant. The sum of that must remain constant. So that once they've collided, let's say a big ball collides with a small ball. The big ball won't be affected much because it has a big mass. The small ball will be shot off. So because it has a small mass, it's easier to change direction. So all these formulas, which I'm not going to go into any further, is really first we separate them, and then we basically update their velocities based on these formulas that come from physics. In here, down here, you can also see that the factor of elasticity plays a role. When balls collide, elasticity tells us by how violently they rebound. Okay, so this is checking for collisions. We check each ball with every other ball once. We apply all these formulas only if they are actually colliding. Once we've done that, we check that they're still all on screen, And lastly, we update their velocities and their positions. This is actually the simplest part, but there it is. And then the last part is simply to redraw the balls. So let's see what redraw does. Redraw is a simple routine that says clear the canvas, set the pen color to be black. For each of the balls, draw a little circle. Then we are creating a string T, which is simply this string, time, colon, space, and a floating point with 2 decimal digits after the decimal point, based on the time that is elapsed. So this is elapsed time. Then it uses this routine, standard draw.text left. At this position, it draws the string T and it displays the screen. Before, when we did animation, we actually put in a delay here. So standard draw.show 20 or 10. And that would show the screen and actually wait 10 milliseconds or 20 milliseconds. But this time we're waiting 0 milliseconds. And that is because the delay is taken care of by this while loop we had at the start. It will carry on and do nothing until it's time to do the next update. So in some sense, this is replacing the delay that we previously used to put in standard in draw.show. Okay, right, so that's the whole program. Now let's fool around a little bit. I'm going to change the gravity. I'm going to make the gravity 10 times stronger, 5 times stronger. Let's go 5, and let's see what happens. And this is important. When you have a program that you don't quite understand the influence of all the variables, it's a good thing to play around and change them one by one so that you understand what is going on. So let's see if this is really works. Will they now fall faster? I can't really see that they have. Will they be pulled down more? Oh, look, they go up a lot. Maybe. Okay, I'm going to shut that down, and I will make it 10 times more. Just want to see an effect. Okay, this time they seem to be full. Maybe they bounce up a lot more, I think, than before. Okay, can't really see that. Okay, maybe gravity is not that important. Let's see what happens if we add a wind factor. Let's add a 0.1 there. So I'm expecting to move sideways now a little. Maybe these numbers are too small. I don't think that moves sideways at all. Oh, it's because I'm not changing the original program. I'm changing this one. I should change the .java. Okay, right. See, the colored one doesn't really run. Okay, let's change this. We start again. Gravity much stronger. No wonder we didn't see. Oh yes, they're falling like lead balls now. Okay, right. And also moving faster because there's more energy in the system. That energy comes from this external force, gravity, that is being applied to all the balls. Okay, fine. That was quite strong. Okay, let's make that 0 and let's put in a wind factor of 0.02. Now I want to see them move sideways. Oh yes, they're being blown against this wall, and in fact it's stronger than gravity, so it's keeping some of the balls up, pinned against the wall. Oh wow, okay. But if gravity is stronger, I expect they'll fall down a little more. Look, that ball is almost about to fall. These balls are almost about to fall, but the wind is blowing so strong that they are stuck to that. Okay, let's make this 0.1 and this 0.2. So now I expect them to come to the bottom, even though they might still be blown to the right. Still being blown to the right. And they bounce back against the wind. But they do tend to lie a little lower. And I think they're jittering more because of the wind. We are introducing extra energy into the system. Okay, I'm going to change that back Okay. Now I'm going to make the bounces very inelastic, 0.4. So that means that when two balls bounce, it'll inhibit them a lot. Let's see if we can see the effect. They don't bounce back very far when they collide. Yeah, there was much less bounce there. And let's add some bounce to the system. I'm going to turn that back into, make that 1.1. Now we expect them to bounce a lot, and in fact this is unrealistic. This never happens in real life. When two things collide, they always lose energy because of noise and heat and sound or deformation that they produce. Having this big an elastic component may actually it's putting new energy into the system, so the balls might never stop bouncing. They might bounce forever. I'm shocked. Okay, right. They're bouncing so much. Okay, what has happened is that I don't know what has happened. I don't know where the balls have gone. Okay, right, but this is clearly not a good idea. What's the other thing I wanted to change? I wanted to change their size. That's the last thing I'll change. So I'm going to have big balls. So at the moment we divide the minimum dimension, width and height, by 35, which means each ball can be at most 35, 1/35 of the width or height, whichever is smaller. But now I'm going to change it to 5, so we'll probably have a lot of big balls. Gravity is normal. I put everything back to normal. Oh, very disappointing. 5 balls is not. Well, let's make it 15. I should have about 20 more. That's more than 20. But yeah, that's actually quite boring. I'm going to make this 50. I'm going to change the starting balls to 1,000. Now I won't see 1,000 balls, but I'll see many more than I had before, and it'll probably be very slow. No, it's not that slow. I mean, this is chaos down here. They're just jittering so much, and the one jitters the next and the next and the next. That doesn't look good, so I'll change it back. But that's interesting to know I can control that. And I said that was the last thing, but I actually want to slow the balls down. So I'm going to make this 2, I'm going to make 0.5, and I expect them to move 4 times slower, almost in slow motion. Well, I think it's more than 4 times slower, maybe. But definitely yes. From the ball's perspective, I've slowed down time by making that time constant a lot smaller. So originally the idea was that this simulation should also include other objects like shelves or rectangles, other fixed objects that the balls can bounce at. They can roll down a slope, for example. And at one time I did add that, but I decided to not complicate things too much. Okay, that's the balls program. I'll link this on that balls page, and it's fun to play around with this simulation. I mean, there's a lot of things you can change, but it gives a good idea of how many programs that look quite exciting actually turn out to be quite boring on the inside. So, like most things on a computer, this is just in a loop, updating a lot of variables and then drawing them on the screen. Good.